Hello guys, this is Justin Bibilan and welcome to this episode of Don't Panic, It's Organic.
Hello guys, welcome back to my YouTube channel. This is Jason Bibilan, aka Denzon118, and welcome to this episode of Don't Panic, It's Organic. So last episode, we discussed about the alkenes, reactions of alkenes, or definitely we discussed about unsaturated hydrocarbons, which actually compose of alkenes that contains a carbon-to-carbon double bonds, alkynes that contains carbon to carbon triple bond. And also, we haven't discussed yet the next unsaturated hydrocarbons, which will in turn, which will be our next lesson or for today's lesson. I mean, okay. So for today's lesson is the last lesson for unsaturated hydrocarbons, which are actually called the aromatic hydrocarbons. So what are aromatic hydrocarbons? So basically, it's from the root word aroma because in 19th century, scientists discovered or isolated compounds, organic compounds, which actually contains a pleasant smelling resins of tropical trees. And because of this, they actually exhibited a smell like something like a pleasant smell, which are actually from the root word, which is aroma. It contains its aroma. Okay, so that's why it actually calls aromatic because of its pleasant smelling. That is actually on the early of the 19th century, and because of this, they actually found out that these aromatic hydrocarbons have high degree of unsaturation, just like your alkenes and alkynes. However, the degree of their unsaturation is actually exhibited chemical stability than their composition would predict. Because when aromatic contains double bonds just like your alkenes, however, because of its high degree of unsaturation, it's actually uh, it's actually exhibited chemical stability than the composition of alkenes. Okay, so it's because uh, these aromatic hydrocarbons contains of what we call a benzene ring. So what is this benzene ring? So by the way, so when I say about I talk about chemical stability, it's because if you have your normal alkenes and if you are going to brominate it using your Br2, okay, so you can actually form a dibromo, okay, a dibromoethane. You have your alkene, which is actually an ethene. Then you are going to react it with the bromination, just like what I have discussed when I discuss about reactions of alkenes. You have your bromination test. Okay, it actually decolorize your bromine because of reactivity of your alkenes. Okay, so from color orange, it turns to be decolorized or it turns to be transparent. Okay, because of the reactions of alkenes. However, if you are going to react or brominate your Br2 at normal condition with your aromatic hydrocarbons or with the benzene, so this is actually the benzene. This one here is a benzene. If you are going to react this with Br2, or if you are going to undergo bromination, your benzene, there are actually no reaction. Okay, because your aromatic hydrocarbons have its own exhibited its own chemical stability. It's a very stable structure that it will not react with Br2 at normal condition. Okay, it should have been something that would be needed so that there should be a reaction between your aromatic benzene and your Br2. Unlike your alkenes, your normal alkenes can actually react with your Br2 at normal condition because your alkenes are very reactive. While your aromatic hydrocarbons, which contains the benzene, it's a very stable structure. It's a very stable molecule, and therefore it can't react readily with your Br2 at normal condition. And there should be an input of another substances that could activate your ring in order for the reaction to proceed. Okay? So this is the structure of the benzene. Okay, so we can actually draw the benzene like this letter A, or the simplified for letter A would be your letter B. Okay, so letter B is the simplified form for letter A, or we can also uh, draw the structure for benzene using the letter C, which actually a simplified form for that is actually for the letter D. Okay, so it's nice that you can also draw the structure for benzene for just like the drawing for B and D. And for letter A and C is that you are going to show all the hydrogens, because in the reaction, if you don't want to be confused by the reactions, you can actually draw, or you can actually present the hydrogen in the in the structure. Okay, so what are the structure and properties of benzene? Okay, according to Prediciculi, he proposed that the structure of benzene is actually a conjugated structure, a conjugated system. You say conjugated, it contains an alternating single and double bonds around the ring. Okay, you notice the structure for benzene. It actually contains a carbon-to-carbon double bond, and you have your single bond, double bond, single bond, double bond, and another single bond. So this is what we call a conjugated system. And mostly conjugated system are those compounds that contains a conjugated structure or conjugated system exhibited a chemical stability because of resonance. So when we talk about resonance, it's actually delocalization of electrons. When you say delocalization, your electrons are actually moving. For example, on this aromatic benzene, the electrons are actually moving around the ring. So we will know about that when we study the structure that is proposed by Friedrich Kikuly. Okay, so you take note that a conjugated system contains an alternating single double bonds around the ring, and it proposed a chemical or exhibited a chemical stability because of resonance. And when we say resonance, there is what we call delocalization of electrons. I repeat, delocalization of electrons. Okay? So when we say delocalization, your single or and double bonds shift position rapidly. So how did Kikuly propose that? So this is what we call the resonance. Okay, so this is what we call a delocalization of electrons. Okay, so your double bonds can actually move there to form this double bond, and that double bond will actually move there, or that electron, I mean electron, will move there. So that is what we meant by delocalization. Okay, there is what we call the movement of electrons. It is not localized, but rather delocalized. Okay, so that electron there will move there to form that double bonds, and that electron there will also move there to form that double bonds. That's why we can depict, or we can show the structure of a benzene by just putting a circle on the inside the ring. Okay, because of the resonance hybrid, because of the delocalization of electrons. That's why we can just draw a hexagon, then draw a small circle at the center, and that would be the structure, or the drawing of the structure of the benzene. Okay, we can show the structure of benzene by just uh, that structure that you just gonna draw an hexagon with a circle at the center. Okay, and of course these carbon to carbon double bonds are actually sp2 hybridized. Okay, so when we say there's actually an sp2 hybridized, the empty p orbital of that carbon is actually uh, empty. Okay, so they are actually empty. This actually empty p orbitals of the carbon, and because of these empty p orbitals, it actually forms a sideways bond to both of these p orbitals. So it actually have a sideways overlapping of orbitals because of these empty p orbitals. Okay, so there is an overlapping of this overlapping of orbitals between the p of this carbon and that p of another carbon and that p of the carbon and this p orbital of another carbon, and so on and so forth. Okay, this 6 carbon has empty p orbital because it's an sp2 hybridized, and therefore it forms a sideways overlap, and it forms what we call a pi bonds. Okay, so a sideways overlap is what I have discussed when you talk about alkenes. When you say sideways overlapping of orbitals, there is what we call a pi bond. And this pi bond, because of this pi bond here and also at the top and also at the bottom of the orbital, it actually forms of what we call an electron cloud, which is actually a pi cloud. That's why it is a very stable structure because of the presence of a pi cloud, or what we call the sideways overlapping orbitals of your p orbitals or MKP orbitals. However, the sp2 hybridized orbitals will actually form a pi bond, or what we call a single bond with your carbon to carbon. No, it's not a single bond, but rather a sigma bond. Okay, a sigma bond will form between your carbon to carbon bonds. Okay, remember that your carbon to carbon double bond contains a pi bond and also a sigma bond. Okay, so this is what makes a benzene unique on its property, because it's actually very stable, and it needs to be activated first before a reaction will proceed. Why is it stable? Because of its resonance hybrid, because of the delocalization of electrons, and also the formation of the sideways overlapping of p orbitals and the formation of a pi cloud. Okay, so that's it. So now let's proceed to how do we name aromatic hydrocarbons. So basically, our main interest is the benzene itself. Okay, there are actually several ways on how we name aromatic hydrocarbons. So let's move on to the first names or naming of the aromatic hydrocarbons. So there are actually some special names and common names of uh, aromatic hydrocarbons. So let's move on. So you have also what we call the benzene derivatives, okay? Because their family or parent compound is actually the benzene. And there is what we call a substituent that is attached to the benzene. So remember your benzene, that's what I have told you earlier, that Kikuli proposes that because of the rapid shifting position of the single and double bonds, we can actually depict or show the structure of a benzene by drawing of a cyclohexane and a circle at the center. Okay, so this is now your benzene structure. And if it is going to be attached with your NO2, and this is what we call a nitrobenzene. Okay, be familiarized with this because it actually these actually are so familiar that that you will that this will actually be shown to some examples, and especially also on the exam. Okay, so a nitrobenzene contains an NO2, a benzene that is attached with your NO2. Okay, so you have your ethyl here. Okay, this is an alkyl. Okay, alkyl benzene. Okay, so you have an ethyl and you have your benzene, so therefore this is an ethyl benzene. Okay, then you have your halogens, which is actually a bromo. So therefore this is a bromine, so this is a bromobenzene. If that is a Cl, then that is a chlorobenzene. If that is an F, then that is a fluorobenzene. Okay? If that is an I, then therefore that is an iodobenzene. Okay. There is also what we call the common names. So please remember these common names because actually these common names are actually used as no, it's not sometimes, but more likely be used as the parent name of the aromatic compound. Okay? So you have your toluene. Okay, so this is a toluene which actually has a benzene with a methyl at the attached to it. Okay, so you can say it's a methyl benzene, but actually the common name for that is that toluene. Okay, that is a toluene. Then you have your phenol. This is actually a benzene attached with an OH. Okay, that is a phenol. So we will discuss more on this when we go to alcohols. Okay, so that is a phenol. Then you have your aniline, a benzene that is attached with an NH2. So aniline. Then you have your anisole. Okay, anisole is a benzene that is attached with a OCH3. So anisole is an example of an ether. Okay, so we will just discuss more on that when we go along with that topic. Okay, so remember all of these common names. You have your toluene, you have your phenol, aniline, and anisole. There are also many common names. Okay, what are all of this? You have your benzoic acid. It is an aromatic carboxylic acid because it contains a carboxylic group, which is COH, and a benzene. Okay, so this is what we call a benzoic acid. Okay, you have your benzaldehyde. Okay, a benzene that contains an aldehyde group, which is C double bond OH. That is what we call a benzaldehyde. Then we have also an orthosilane, which contains 2CH3, which are actually adjacent to each other. Okay, so this is actually a common name, but the IUPAC name for this is actually 1,2-dimethylbenzene. But the common name should be an orthosilane. So I will just discuss more on ortho, meta, and para naming for aromatic hydrocarbons later. Okay, you have your orthosilane, you have your cresol. So a cresol contains an OH and CH3. So while your acylane is CH3 and CH3. So you have your orthocresol, you have your metasilane because it's actually shift in position. This is actually 1,3 now compared to your ortho that is 1,2. Your meta is 1,3. Okay, you have your metacresol that is also 1,3 and this is 1,2. Okay, you have your parasilane which is actually 1,4. Okay, you notice their difference. Okay, and you have your paracresol. Okay, so that is an ortho, meta, and para for that. Okay, I will just discuss that later on. Okay, just remember all of these common names because this is actually being used, not this one, this orthosilane and cresol, but the benzoic acid, benzaldehyde, the aniline, the anisole, the phenol, and also the toluene are actually used as our parent name for a specific compound. Okay, so when two groups are present, so as we have shown earlier, there are actually two groups. Okay, for example, this one, these are actually two groups already. Okay, when two groups are present on the ring, three possible orientations exist. Okay, so what are these three possible orientations? You have your ortho, the meta, and the para. Okay, remember this, you have your orthosilane, you have your metasilane, and your parasilane. You have also an orthocresol, metacresol, and paracresol. So that's what we meant by three possible orientations exist. So when two groups are attached to the benzene, then there are three possible orientations. And they may be named by either the IUPAC nomenclature. So we will discuss IUPAC nomenclature system or what we call the numbering system or the common system of nomenclature. So the common system is what we call the ortho, meta, and para system. Okay, so that is the naming for the common names. You have ortho, meta, and para. Okay, for IUPAC, that is what we call the numbering system. The 1, 2, 1, 3, blah, 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 etc., etc. Okay? Okay, you have your two groups. So if both of these groups are actually adjacent to each other, that means They're actually just beside, okay, of you can also put the G there. That is actually the same, okay, if the G is there. Am I right? So it's actually the same that you're going to put the G there. We're going to put the G. Okay, that is actually the same. That is also an ortho. Okay? So the IUPAC name is number, like 1 and 2. Or this is 1 and 2. Okay? But the common name would be, this would be an ortho position. Okay? So the IUPAC is 1, 2, while the common name is an ortho position. You can just write an italicized O, or you can also write the word ortho for that. Okay? So your meta position, okay, your meta is actually found here. So if this is your substituent number 1 or group number 1, it actually, the meta position is actually found on the substituent in carbon number 3. Okay? So that would be a 1, 3. Or you can also write the G here. That is still the same. That is actually a meta position. Okay, that is 1, 3. You have 1, 2, and 3. Or if the substituent is actually found on there, then that would be 1, 2, and 3. That is still 1, 3, or the meta position. Okay? Then your para position is actually a 1, 4 on the IUPAC system. Okay? So you have 1, 2, 3, and 4. So that would be the position of a para. Okay? You can also say that if you have the G there, for example, if you have the G, then the para position would be actually there. Okay? That is still correct. That is actually also a para because that is 1, 4. 1, 2, 3, and 4. Okay, so more of that example when we go to the naming already.